Assalamu alaikum. My name is Nimra Meen. I am the student of MS Chemistry at the University of Management and Technology. Today, the topic of my presentation is liquid nitrogen, and I prepared this topic in the supervision of Dr. Hammad Majeed. So, what is liquid nitrogen? Liquid nitrogen basically is liquefied form of the element nitrogen, and it is often denoted as Ln2 or Lin. History. Liquid nitrogen was first discovered in a stable state in 1883 by Polish physicists Zygmunt or Karol Olszewski and Kazimierz Robiski. These scientists deserve a note for their groundbreaking work in understanding this cryogenic liquid. Physical properties. It obtained industrially through fractional distillation of liquid air. Liquid nitrogen has a boiling point of approximately minus 195.8 degrees Celsius, and if we talk about in Fahrenheit, that will be minus 320, and in Kelvin it will be 77. Key characteristics of liquid nitrogen: colorless and mobile, non-toxic and inert, not flammable, slightly lighter than air, soluble in water, and viscosity is about 1/10 that of acetone. Freezing point. It will chill at minus 210 degrees Celsius temperature. Diatomic nature. Even after liquefaction, nitrogen molecule remain bonded as N2. Occurrence of liquid nitrogen. Liquid nitrogen doesn't occur naturally. We create it artificially from the air. It's primarily composed of the nitrogen molecule and is obtained by cooling and condensing gaseous nitrogen. The process involves compressing and cooling air until it liquefies, allowing us to collect the liquid nitrogen. Reason for extreme cold. Liquid nitrogen's extreme coolness stems from its molecular behavior during the transition from gas to liquid. As nitrogen gas cools down, its molecules slow down and come closer together. Eventually, they condense into a liquid state at its boiling point of approximately minus 196 degrees Celsius, minus 320 in Fahrenheit. Liquid nitrogen is incredibly cold and can freeze objects on contact. Representation. Liquid nitrogen is often denoted by abbreviations such as Ln2, Ln, or Lin. These abbreviations are commonly used in scientific and industrial context. Inverse Leiden force effect. Definition. When a liquid Leiden force effect. Leiden force effect is a captivating phenomena observed when a liquid like water, or in this case liquid nitrogen, encounter a significantly hot surface. Here how it works. The surface temperature must be much higher than the boiling point of the liquid. When liquid nitrogen touches the hard surface, it vaporizes rapidly, creating a vapor layer like a cushion between the liquid and the surface. This vapor layer insulates the remaining liquid from direct contact with the hard surface. The result is sputtering sound and an intriguing visual effect. However, due to the Leiden force effect, liquid nitrogen's effectiveness as a coolant is limited. When it encounters a warm surface, it vaporizes quickly, relying on the vapor layer to protect the remaining liquid. Inverse Leiden force effect. The interaction between a liquid drop initially at room temperature and a bath of the liquid nitrogen. In this scenario, heat transfer occurs through film boiling. A nitrogen vapor layer develops that may cause the drop to levitate at the wall's surface. Phenomenology of this surface inverse Leiden force effect. Investigating the effect of the drop size and density by using an aqueous solution of an tungsten salt to vary the drop density. So by finding that depending on its size and density, a drop either levitate or instantaneous sink into the bulk nitrogen by measuring the duration of the levitation as a function of the radius r and the density AD of the liquid drop. Observe that the levitation time increases roughly linearly with drop radius but depend weakly on the drop density. However, for sufficiently large drop r greater than equals to Rc rho d, the drop sink instantaneously. Levitation does not occur. The sink of a relatively hot droplet induces film boiling, releasing a stream of vapor bubbles for a well-defined length. Her Johann Gottlieb Blendenford's discovery in 18th century continues to captivating scientists and curious minds alike. Liquid nitrogen's unique properties make it a valuable tool in various fields, from cryogenic to culinary experiments. Here I show the diagram, which is simplified configuration for the floating of a water drop on the surface of liquid nitrogen. Here you can see that capital R represents the radius of the sphere and L is the thickness of the nitrogen vapor, and we know that will be r theta is the angular velocity and depend on r and theta. The sphere float on the Ln2 surface because the weight of the sphere is balanced by the vapor phase of the nitrogen gas. Here you can see that Tf is equals to Td plus Ts over 2, where Td is the temperature of the drop and the Ts the saturation temperature of the liquid nitrogen. We made a simplified model to understand the levitation of the water drop on the surface liquid nitrogen. The curvature of the liquid nitrogen under the sphere is assumed to be hemispherical, as you can see in figure 1. Figure 1 shows the diagram for the levitation of a water drop on the surface of liquid nitrogen. The force spelling equation, the weight of the sphere with the vapor force and the surface tension force, is given by straight Ws is equals to Fv plus F sigma, where Fv represents the vapor force of the nitrogen gas. The weight of the drop is Ws is equals to 4 over 3 pi r cube rho dg, where r and rho d are the radius and the density of the drop respectively. The surface tension force is F sigma is equals to 2 pi r sigma. Any instant of time, the sphere is at every temperature Td and the evaporated liquid is assumed to be the at saturation temperature Ts. The properties of the fluid are evaluated at the film temperature Tl. The model has complete symmetry with respect to the angular coordinate and the radial component is dominant. The following continuity and momentum equation can be written as partial P over partial T plus delta multiplied by rho V is equals to 0. That will be equation 5. And here delta P will be equals to theta V delta square V. That is equation 6, where NV is the viscosity of the nitrogen gas. We introduce the average vapor velocity. U is equals to 1 over L integration r over r plus v naught dr, where L is the film thickness and r is the radius of the sphere. The following boundary condition apply to the continuity and the momentum equation. Here you can see equation number 8, u is equals to 0 at theta is equals to 0. When r small r will be equals to r, then v is equals to 0, and v is equals to 0 if r is equals to r plus 1. P is equals to 0 at theta is equals to pi by 2. These are the conditions of the equation, where you can see that partial over partial theta u sin theta is equals to omega sin theta over 2 pi rho pvl, where omega is equals to partial m over partial t is the evaporation rate of the liquid nitrogen. If the boundary condition in equation 8 is applied, the average vapor velocity from equation 9 became u is equals to minus omega over 2 pi rho v summation multiplied by cos theta minus 1 over sin theta. From the momentum equation number 6, we got 1 over r partial p over partial theta is equals to neta v over r square multiplied by rho v over partial r, where we have considered only the radial component, which is the dominant term. If the boundary condition equation 8 is applied, the vapor velocity from equation 11 became theta v theta is equals to 2 r n v or multiplied by partial p over partial theta multiplied by r minus r multiplied by r minus r plus 1 over r. That is equation number 12. Where theta is the surface tension of the liquid nitrogen, The following assumption is calculate the vapor force are made in developing the model. The conveyance the integral circulation of the sphere is assumed to be negligible, and the radius heat transfer which become dominant at high temperature can also be neglected in our theory. The major model of the heat transfer is conduction. The flow of vapor is considered to be laminar and incompressible. The vapor, the velocity, and the temperature profile are assumed to be steady state. As we expect, V naught became 0 on the surface of the sphere and on the contact surface of the liquid nitrogen with equation 12, the average velocity became U is equals to minus 1 over 2 neta V multiplied by partial P over partial theta multiplied by capital R. From equation 10 and 13, we get partial P over partial theta is equals to omega NV over partial PV multiplied by L R scale multiplied by cos theta minus 1 over sin theta. That will be equation number 14. From equation number 14, we can define the pressure in terms of P theta double slash is equals to omega NV over partial PV L R scale, and here we apply integration which will be condition having condition theta double slash pi over 2 cos theta minus 1 over sin theta d theta. So it will become equation number 15. As so the vapor pressure can be expressed as Fv is equals to integration delta dp theta double slash dag, where dag is equals to 2 pi r square sin theta d theta in the surface area of the sphere containing the liquid nitrogen. We can define equation number 3, that is F theta double slash is equals to integration theta pi over 2 double integration theta slash pi over 2 cos theta minus 1 over sin theta d theta sin double slash theta. That will be equation number 17. With equation 17, the vapor force in equation 16 can be expressed as Fv is equals to 2 neta V over PVL multiplied by omega F theta double slash, where the value of the F double slash is 0.39. The vapor force is proportional to the evaporation rate of the liquid nitrogen and inversely proportional to the thickness of the vapor cap. The evaporation rate can depend on the temperature of the sphere. The heat change can be expressed as general form. The rate of the heat exchange between the film and the liquid nitrogen that will be different. As you can see that delta Q is equals to heat change is equals to M over L partial T minus T melt plus Cp delta T. That will be became equation 19, where delta is the delta function, partial is the delta function, T melt the melting temperature of the drop, L the latent heat of the drop, and Cp is the specific heat of the drop at the constant pressure. According to equation 19, the rate of the change for the drop equation is equals to partial theta over partial q over partial t is equals to mcp partial t over partial t, and t can't be equals to t melt plus ml, t is equals to t melt dt. The rate of the heat change for the vapor film can be written as partial Q over partial T is equals to HA delta T, where film heat transfer coefficient H is given by equation 11. H is equals to kV over R plus multiplied by 2P rho dVq 3L over 9 theta VR multiplied by TD minus TS multiplied by 1 over 1 plus CV delta T over T 2L, and the whole equation 1 over 4. With kV being the thermal conductivity of the vapor, rho d the density of the sphere, Cv the specific heat of the vapor, and Td and Ta the temperature of the sphere and the liquid respectively. The rate of the heat change on the liquid nitrogen which at saturation temperature is the rate of the change of between the film and the liquid nitrogen is HA delta T is equals to L partial M over partial T. The vaporization rate can be determined by assuming uniform sphere cooling. The evaporation rate change with the sphere temperature for the uniform drop cooling. The temperature of the water drop has down from the initial temperature to 0 degrees Celsius due to the latent heat. As you can see that in equation number 16, T T is equals to mCpD multiplied by T initial minus T melt over HAD T melt minus TS, where CPD is the specific heat of the sphere from equation 24, the evaporation rate for a drop that is could from the initial or to the melting temperature. So equation number 17, partial M over partial T is equals to HAT d over 2L T melt minus Ts. If the latent heat is considered, the time is froze, the entire sphere uniform is T melt is equals to M ice L over HAD T melt minus Ts, and the evaporation rate during this process is partial M over partial T is equals to HA d over 2L T melt minus Ts. That will become equation number 29. With equation 24, the time for the sphere's temperature to go down from the melting to the latent force temperature, that is Td is equals to rho P Cv ice over 3H in T melt minus Ts over TLP TF minus Ts. And you can see that we conclude that T initial minus T is T melt minus T is T melt minus T is E minus T over T for T initial less than equals to TD less than equals to T melt. For TD is equals to T melt for and T melt minus TSC E minus T over T for T melt less than equals to TD less than equals to TLF. That is equation number 33. And at the last we get the equation. You can see that T is equals to 2R rho d over 3H multiplied by CPD in T initial minus T melt plus L over T melt minus TS plus 0.9 Cp ice over 2 ln T melt minus TS over TLT minus TS. In conclusion, we conclude that we show a force balance equation in which the weight of the water sphere was balanced by the surface tension liquid nitrogen and the vapor force of the nitrogen gas. The vapor force was calculated by considering the dominant radial term and assuming uniform cooling of the drop in three different steps: the initial temperature of the drop to the melting temperature of the drop, the melting temperature due to the latent heat, and then the melting temperature to the latent force temperature. The total floating time of the water drop on the force of the on the surface of the liquid nitrogen was expressed in terms of temperature change of the drop at each step. The water drop fallen when the temperature decreased to the latent force temperature, at which the vapor force became weak due to bubble formation. Here is the theory of the latent force effect, where when the density of the sphere is higher than that of the sphere sporting liquid, we can think of two kinds of the floating mechanism: wetting and non-wetting. For the wetting case, the surface tension of the liquid and the abrasive force support the weight of the sphere, where for the non-wetting case, the vapor force coming from either the drop or the encompassing liquid and the surface tension force support the weight of the sphere. Our case is non-wetting one, and the basic model for the floating sphere on the liquid include the nitrogen vapor film separating the sphere and the supporting nitrogen liquid. A drop of water float on the liquid nitrogen surface. When a sensible heat of the floating sphere evaporates the encompassing liquid, the heat passes from the warmer sphere drop and evaporate the liquid nitrogen beneath it. Liquid air distillation. The primary method of the producing liquid nitrogen involves liquid air distillation. Here show how it works. Air composition. Ordinary air comprises approximately 21% oxygen and 78% nitrogen and trace amount of the other gases. Compression. The process begins with compressing the air is using a piston. This compression helps inject the air into next stage, cooling, and then condensation, volume reduction, which will be at 700 liter of gaseous air condensed to just 1 liter of the liquid air. And then last one is separation. The liquid air is further separated to extract pure liquid nitrogen. Homemade liquid nitrogen generator. Step 1. The liquefied generator has a few basic components starting in order. Creating a homemade liquid nitrogen generator. Here is some component and step involved in this formation. as you can see in the diagram. Compressor filter, basically it is the component of making homemade liquid nitrogen. And third one is compressor. Indeed, the compressor is a critical and often costly component in a homemade liquid nitrogen generator. Flow rate. A high flow rate result is a faster cool down and increased production rate. When the gas is compressed quickly, it cools down more rapidly during subsequently expansion. High pressure. Having a high pressure compressor allow for a large temperature drop during the throttling process. Throttling refers to control expansion where the gas transition from high pressure to low pressure. The greater the pressure difference, the more significantly the temperature drop. Refrigerator compressor. While a regular refrigerator compressor can be used, it has limitation. Lower pressure, less efficient, ambient to cryogenic temperature, and you can see that I have mentioned here it will be minus 320 degree Fahrenheit or 196 Fahrenheit degree Celsius. Step 4, that is scramble. Creating a homemade liquid nitrogen generator involves some intricate step and your detailed breakdown is impressive. Scrubber construction. The scrubber's purpose is to remove impurities like carbon dioxide and water from the gas stream. Without this step, these components could freeze and clog tubing and valves. Zeolite molecule sieve. Zeolite is a naturally occurring fine porous material. You use 30x molecule sieve and added some 4A sieve material with the color indicator. Filtering and assembly. To prevent zeolite from getting sucked into the compressor, cut a disc of 200 micron screening. This hold the material is placed while allowing airflow between the 4 to 2 inches reduce and the couple fitting glued the screening. Scrubber input. The top of the scrubber requires 3 input: fresh gas input, regenerated gas, reduce the need for flash N2, excess gas vent, allow any excess gas to escape. Step 5 is pre-cooler. Creating a pre-cooler for your homemade liquid nitrogen generator is a crucial step to remove excess heat from the compressed gas. Pre-cooler overview. Pre-cooler purpose is to cool down the hot compressed gas before it ensures the next stage. Coil of tubing. Your pre-cooler consists of long coil of tubing. You have used 20 feet of 1/4305 stainless steel with the 0.035 wall thickness. Aluminium fine. To enhance heat transfer, you have to add 0.016 thickness aluminium fine to the tubing. These fine increase the temperature gradient TD over TD, allowing better cooling. Your melting approaches, drilling holes and securing the fins ensure efficient heat exchange. Step 6 is regenerating cooling tower. Creating a homemade liquid nitrogen generator indeed involves meticulous work and your detailed breakdown is commendable. Helical coil and needle valves. The compressed gas enters the tower through a long helical coil. Upon re-expansion, it passes through a needle valve at the end, directing it into reservoir. The cooled gas that didn't liquefy return in via Teflon tubing. High pressure fitting and adapters. The end of the tubing need high pressure stainless steel fitting and adapters. Throttle. That's step 7, that is throttle. Fine control. The large level provides better fine tubing of the orifice opening. Standard knob handle can be too small for precise adjustment, especially when dealing with extreme cool temperature. Frozen knob challenge. As the temperature dropped during a turning a small knob became challenging. The knob can freeze in position, adjusting difficult. By using a large level, you have effectively addressed this issue. As you can see in the diagram, step 9, that is reservoir. Reservoir function. The reservoir holds the collected liquefied gas, whether it's nitrogen or air. Your choice of stainless steel vacuum bottle is practical and efficient. Adapter and the Teflon tubing. The key lies is fascinating an adapter that directs the expanding gas to the generation Teflon tubing surrounding the high pressure stainless steel tubing. The buffer connect to the output of the needle valves. The inflow out to valve connect to a tube fitting on the end of high pressure tubing. A small screw secured the Teflon cylinder, preventing the expanding gas from pushing it off. A small tube of Teflon gas goes from button of the thermos to the outside through an insulated jacket, allowing the liquefied gas to escape. A small plug keeps the liquid containing until you are ready to drain the system. Summary. This project allows an individual to do what only commercial industry has done in the past. You can generate your own liquid air or nitrogen with a high production rate. The cool down period depends on your compressor, length of regeneration, tubing, and how well you can insulate your system. There are some following steps used in the production of liquid nitrogen. Hazards. Extremely cool liquid nitrogen play a vital role in research as we know that liquid nitrogen is an extremely cool liquid and it rapidly freezing skin tissue, eye fluid, resulting in cold burn, permanent eye damage, etc. Asphyxiation. 695 times we can expand liquid nitrogen in volume during vaporization. Its color order is not harmful. If sufficient liquid nitrogen is vaporized to reduce oxygen percentage to below 19.5%, there is a risk of oxygen deficiency, which may unconscious and death may occur. So ventilation is so much important. Oxygen enrichment. Surrounding environment. During the transformation of liquid nitrogen, there is also nitrogen present in the surrounding environment. As the oxygen-enriched cryogenic container system return to ambient temperature, the nitrogen evaporates more slowly than oxygen. Compact and versatile. Liquid nitrogen serves as a compact and readily transported source of the dry nitrogen gas. Unlike other gases, it doesn't require pressurization. Its remarkable ability to maintain temperature far below the freezing point of water make it invaluable. Applications. Here some general application of liquid nitrogen. It's used as cryotherapy, in laboratory work, in cryogenic, cryosports, fire prevention, dry nitrogen gas, food industry, and in blood cryopreservation in cocktail preparation. Uses. Liquid nitrogen is a compact and readily transported source of dry nitrogen gas, and it pressurized further. Its ability to maintain temperature far below the freezing point of water make it extremely useful in wide range of applications. It's used to store cell at low temperature in laboratory. It is also used in cryopores to demonstrate rapid of freezing by evaporation as a backup nitrogen source in hypoxic air fire prevention system, as a source of very dry nitrogen gas for immersion, freezing, and transportation of food product. For immersion, freezing, and transportation of food product, for the cryopreservation of blood, reproductive cells, and their biological sample and materials. To facilitate cryoconservation of animal genetic resources, to freeze water and oil pipe to work on them in situation where a valve is not avail- available to block fluid flow of the work area. For cryogenic preservation in hope of further reanimation, for shrink fitting machinery put together. For cryonic preservation in hope of future reanimation open as a coolant. For CCD cameras in astronomy to maintain a low temperature around the primary liquid helium cooling systems, for vacuum pump tap and in control evaporation process in chemistry as a component of cooling bath used for very low temperature reaction in chemistry, for computed and extreme overlooking, for simulation of space background in vacuum chamber during speculation thermal testing to control the temperature of mass concrete. In food of preparation in containing inserting and pressurization by injecting control amount of liquid nitrogen as a cosmetic convective giving a smoky bubbling effect to drink. In turning construction to stabilize unstable and loose terrain, liquid nitrogen injected into soil to freeze the vapor water present in the soil. With increased bearing capacity and impermeability, the improved ground will not collapse during excavation and subsequently walk. Liquid nitrogen industrial application. Absolutely, liquid nitrogen is indeed a versatile substance with widely area of application across various fields. Cryogenic. Liquid nitrogen play a crucial role in cryogenic application. It is used for preserving biological sample, freezing tissue, and even superconducting magnet. Backup nitrogen. In fire prevention system, liquid nitrogen serve as a backup nitrogen source. By reducing the oxygen concentration, it helps prevent fires. Shearing welding of machinery. Liquid nitrogen is employed for shearing welding. It cools metal components rapidly, allowing them to fit together precisely. Especially popular in food industry, its uses. Its use has detailed all the way back to the late 1800s. In more modern time, liquid nitrogen rapid chilling hard made it extremely beneficial. Nowadays, it is even being used to quick freeze cocktail and chill glasses, create a fun, smoky presentation for food and drink, and in the ever trendy world of molecule gastronomy. And second point is that is as a use as a company with a great deal of experiences with the other gases. We have four bulk carbon dioxide trucks. We are very excited to know how a bulk liquid nitrogen trailer. This will allow countless clients to use liquid nitrogen for food processing purpose as well as many others. For instance, we have one client that use liquid nitrogen in soda bottles. The nitrogen make the bottles expand and help increase the strength of the bottles, allowing for better stickability, and another customer uses it make to its ice cream. Due to the formation of smaller ice crystal because of the liquid nitrogen, the product used is smooth because of it. This new trailer means we can offer bulk supplies to our customer. Whatever its use or purpose, fun or function, food or industry, you will find the bulk liquid nitrogen supply to be just what your company needed. Construction and maintenance of public work. Liquid nitrogen is used to temporarily freeze a section of pipe and thus prevent its content from spilling out when opening it to carry out some work. It can also be injected into an area where a crack has been covered with sealing material, producing a plug of frozen matter to buy time and let the repair the fixed. In welding, it is also used for manufacturing electronic component and the shielding gas processes. In laboratory for various fields, it is used to remove solvent or water. In medical, it is used in medicine. In cryogenesis, subjecting abnormal tissue like tumor or warts to extreme cold for removal. To store semen, liquid nitrogen is used to conserve and store semen both animal and human. For vegetable and animal product which enable preservation and transportation, it is also commonly used for making ice cream and cocktail. In pharmaceutical industries, the production in various processes, one important application is cryopreservation. It is also used in material like cell, tissue, and vaccines and frozen at very low temperatures using liquid nitrogen. This helps to maintain their viability and integrity over an extended period. Liquid nitrogen is also used in freezing, drying, and process that remove moisture from pharmaceutical products while preserving their chemical and physical properties. Additionally, in cryogenic grinding, liquid nitrogen is used to cool and embrittle material, making them easier to grind into fine powder. In preservation of biological sample, liquid nitrogen is used in the preservation of biological sample by cryopreservation. It involves freezing the sample at very low temperature using liquid nitrogen. This helps to maintain their integrity and viability for long-term storage and future use in research, medical treatment, and other applications. In the preservation of biological sample, liquid nitrogen is used for cryopreservation. This process involves rapidly freezing the sample at temperature below -150 degrees Celsius, -2 degrees in Fahrenheit, using liquid nitrogen. By doing so, the biological activity within the sample is effectively halted, preserving their structure and functionality. Cryopreservation with liquid nitrogen is widely used in fields like medicines, research, and biotechnology to preserve valuable biological samples for future use. As a coolant for superconductors, liquid nitrogen is used as coolant for superconductor because it can reach extremely low temperature. It is necessary for superconductivity to occur by cooling the superconductor with liquid nitrogen. It can achieve and maintain the low temperature required for material to exhibit zero electrical resistance. When it comes to cooling superconductor, liquid nitrogen is commonly used as a coolant because of its ability to reach temperature as low as -196 degrees Celsius. And if we talk about in Fahrenheit, that will be -321. These extremely low temperatures are necessary to achieve and maintain the superconductivity states where electrical resistance drops to zero. By immersing the superconductor is liquid nitrogen. Process for vegetable and animal product, which enable preservation and transportation. It is also commonly used for making ice cream and cocktails. In food and beverages. In the food and beverages industries, liquid nitrogen is used for a variety of purposes. Like it's often used for flash freezing, involving rapid freezing food items to preserve their quality and freshness. Liquid nitrogen can be used to create unique texture and presentation, such as in creation of nitrogen ice cream or frozen cocktail. It is used for cryogenic grinding, where the extreme cool temperature help in grinding spices, coffee beans or other food ingredient into fine powder. Used in creating unique texture of molecule gastronomy. In molecule gastronomy, liquid nitrogen is used to create unique texture in food. It is often used to rapidly freeze ingredients, resulting in interesting and unexpected texture. For example, liquid nitrogen can be used to make instant ice cream with their smooth and creamy texture. It can also be used to create frozen form gels and powders, adding a touch of creativity and excitement to dishes. The extreme cool temperature of liquid nitrogen allows for rapid freezing, preserving the integrity of the ingredient and creating a unique dining experiences. In electronics, liquid nitrogen is used in electronics for cooling purposes. It is used to cool down components like semiconductor and superconductor during manufacturing. The extreme cool temperature of liquid nitrogen help to maintain the stability and efficiency of electronic devices. By cooling these components, it reduces overheating and allows them to function optimally. Liquid nitrogen is also used for shrink-fitting metal parts, where the cool temperature causes the metal to contract and fit tightly together. Overall, liquid nitrogen plays a crucial role in maintaining the performance and reliability of electronic devices. Liquid nitrogen in the treatment of skin diseases. Liquid nitrogen is a satisfactory freezing agent in the treatment of the skin diseases as warts and keratosis, superficial hemangiomas, and all these skin diseases. It is a valuable and easily applied use in describe, and the result of the treatment in 154 cases of the warts are presented. Liquid nitrogen is applied by means of an ordinary cotton swab or applicator stick. To pick up the liquid nitrogen, it is important not to wrap the cotton too tightly on the applicator. This is dipped into the liquid and applied to the lesion to be treated. No appreciable pressure is required for most lesion, and freezing is most instantaneous. Lesion of considerable depth, such as warts on the palmar or plantar surfaces, require several seconds to become frozen to their whole depth. Pronounced hyperkeratosis result in solver freezing since epidermis in good insulators. Use in preservation of dead bodies. The concept of cryopreservation began in the 1960s when Mitchell processed Robert Eating proposed the idea of freezing human in his book. The prospect of immortality. In 1966, the first human body was frozen by being placed in liquid nitrogen and stored at just above freezing. Though that body was thawed and buried shortly after, the next time a body was cryopreserved was in 1967. And that one has remained frozen with the hope of future revival. Since then, about 250 dead bodies have been cryopreserved in the United States. And 1500 people have decided for the cryopreservation of their corpses. Here are some references of this presentation. And that's all. Thank you so much.